worked with towed underwater video and integrated it with Multibeam Acoustics in order to map habitats on the seafloor and assess the fish communities that are there. So we'll just start with a little bit of background on our project. One of the first things we did when looking at a mapping project, we're like, what has already been mapped on the West Florida shelf? And we found that as of 2014, that there was only high-resolution bathymetry for about 5% of the West Florida shelf. And this is despite it being a very commercially important area. There's commercial and recreational fisheries that are worth tens of billions of dollars and support tens of thousands of jobs. So that was kind of surprising. In addition to being economically important, a lot of these areas have been identified as ecologically important. So over here we have the Madison-Swanson area. There's these large pinnacles, and it's a confirmed site for gag grouper spawning aggregations. Over here is the Florida Middle Grounds, which is considered essential habitat for sponges and corals. We have the Steamboat Lumps area over here, which has these grouper holes made by red grouper. And down here we have Pulley Ridge, which is this drowned barrier island that supports a lot of mesophotic reef biota. So with knowing that there's all that important habitat and so much that hasn't been mapped, that begs the question, what else is out there and how does that relate to the fish communities in the area? So over the last several years, the CSCAMP project has collected high-resolution bathymetry data in these areas in purple, as well as doing some towed camera work in order to to start getting at that question. And I'm going to talk to you today about this area over here called the Elbow, and it is a popular offshore fishing area. So the objectives of my thesis were first to develop a semi-automated and objective way of mapping habitats on the seafloor, develop quantitative relationships between fish communities and their abundance and the habitat characteristics, and then use the results from those prior two objectives to estimate the total abundance of various fish within my study area. So how do we map? Well, on land, we have these handy things called satellites, and they fly overhead. They take nice images of things. So here we have St. Pete. It could be like, that green area is some vegetation. That's a lake. That's urban development. But you'll notice we just see water when we look at the ocean. So we can't see the seafloor using satellites. So instead, we have to use sonars. And shown here is a multibeam sonar, which is what we use. And what they do is they shoot out a wide swath of sound, and they primarily measure two things. The first thing is how long it takes for that sound to return, and based on that, you can calculate the depth. And you get what's called the bathymetry surface from that. The other thing it measures is how strong that sound returns, and that relates to what's called backscattering. And this gives us an idea of what the seafloor looks like, but we can't interpret it in the same way as a satellite because they're created using sound rather than using light, which is what our eyes are used to seeing. So in order to interpret those images, we do ground truthing, and for us, that comes in the form of towed underwater video. So pictured here is the sea bass towed camera system. So it's deployed off the back of the Weatherbird here, and we have a schematic representation on that side. It has various different cameras as well as sensors to record the depth, the altitude above the seafloor, various different sensors to record oceanographic variables like salinity or chlorophyll. And we use that to actually observe the habitat and the fish that are down there. When talking about habitat, that can mean a lot of different things to different people. So I'm using the Coastal and Marine Ecological Classification Standard, which is the national standard for describing marine habitats in the United States. Specifically, I'm going to be classifying the substrate and biotic components of habitat. So for substrate, in this area, the main delineations were between sand and rock. And then I further broke out rock into three different relief categories. So you have that low relief area, which is very flat rock. It usually has a bit of a sand covering to it. That moderate relief where you have this step-like change in elevation, and then high relief where it's this very large, steep, and sudden change. On the biotic side, we are concerned with the benthic habitat as we're mapping the seafloor, not the planktonic aspects. And the main distinction here was between bare, which could be sand or it could be bare rock, and habitats with attached fauna, so things like sponges, gorgonians, stony corals. So now we're going to talk about benthic habitat mapping. And again, the two primary data sets that you get from the multibeam are the bathymetry surface, which is the depth, and the backscattering, which is how related to how strong the sound returns. And from each of those variables, you can derive a ton of different things. So on the bathymetry side, a lot of those things describe the shape of the seafloor. They're called terrain attributes. So how is it sloping? What's the curvature? How rough it is? So those are all things you can get from the bathymetry surface. On the backscatter, you have all these weird things that say GLCM. And those are mathematical metrics of texture that look at the texture of the image. On the ground truthing side, I use these three transects from sea bass. So we have that pink transect that goes across kind of that main feature, that green transect that goes through the middle, and then that black transect that zigzags back and forth, and it's meant to go across several different habitat types. And along these transects, habitat was classified from still frames every 15 seconds, and that was used to actually create the habitat maps. I then have this dotted transect here, and that was saved as a validation transect to check how well my maps worked using new data. So in order to relate the sea bass imagery to the acoustic imagery, we need to know where sea bass is in space. We can use GPS satellites to track the boat. However, we can't track sea bass directly because it's underwater. So what we have to do is we need to use the coordinates of the boat and then calculate how far sea bass is behind the boat. So the acquisition software does that with this equation here. It just uses basically Pythagorean theorem, where it uses the cable out from the boat as well as its depth, the depth of the sea bass, and then it has that catenary factor K, which just allows the cable to have a little bit of bend rather than it being just a straight line. And that gives us a lot better positional accuracy than if we were just to use the boat alone. However, there's still some sources of uncertainty, including the exact value of what that catenary factor is, currents that might be pushing sea bass to one side or the other, as well as the fact that we're using forward-facing imagery. So the imagery from sea bass is actually slightly ahead of sea bass rather than directly where sea bass is at any given time. So my solutions to that were first to take the acoustic data sets and make it a bit coarser resolution. The original data sets were in 1 to 2 meter grids, but I wasn't confident that I could match up sea bass imagery with one of those individual grid cells, so I changed the resolution to be 10 meter grids. I also filtered through the ground truth points, so I only included points that were the same as their previous and subsequent habitats, so that if the position was a little bit off, I was still likely working in a homogeneous area and training on the right type of habitat. The third thing I did was I have that validation transect, so I'm not trusting my results. I'm actually testing it on new data and seeing how well it worked. And then those previous two things, the filtering of the ground truth points and the validation, actually required using a coarser thematic resolution, which just means collapsing that up to sand versus rock for the mapping component of this, because those high relief features came in and out of view very quickly, and there weren't as many of them, so it was hard to get a really good position on each of those. So I mentioned I wanted to do this in a more fairly automated fashion, so I used statistical classifiers. The two main distinctions in statistical classifiers are unsupervised versus supervised classification. On the unsupervised classification, those typically rely on clustering algorithms. So you take all your variables, you run it through a clustering algorithm, and then you use your ground truth points to interpret those clusters and figure out what each corresponds to. The supervised classification, that's more like a regression. You have your response variable that you're trying to predict, which is the habitat, and you have your acoustic data sets as the explanatory variables, and you fit a model, and then once you fit that model, you use that to predict out to the entire study area. So we're going to go through what that looks like schematically. First, for the unsupervised classification. Here are your bathymetry and backscatter raster grid data. You then calculate the various derivative features, so those terrain metrics, things like the slope, the curvature, roughness, as well as the texture metrics from the backscatter. A lot of these tend to be really highly correlated with one another, which can mess with the clustering algorithm. So I ran it through a principal component analysis, which provides you with new variables that are all combinations of your original variables, but they have the nicer property that they're all relatively uncorrelated with one another. You also typically limit the number of components you retain just because each one becomes less important than the previous ones. From those, you run it through the clustering algorithm, and you end up with one data layer. So here you can see you have this blue cluster, the green cluster over here, and this brown cluster. And to interpret them, you plot your ground truth points. So you can see that the blue cluster corresponds to habitat 1, the green cluster also corresponds to habitat 1, and the brown cluster corresponds to habitat 2. So you would merge that green and blue cluster as habitat 1, keep that brown cluster as habitat 2. So then when you interpret it, you have this habitat map that looks like this, which is a thematic habitat map describing describing the area in terms of the groupings that you had. So using that on actual data, we're going to run through how I did this for the substrate classification. Again, you have your bathymetry, your backscatter, and all those various derivative features. And you need to fit two things for the unsupervised classification. I mentioned you do a principal component analysis and you only retain a certain number of them. There's a lot of different thresholds people use for how many they retain. What I did was I plotted the variance explained by each component against what you would expect if the variance was randomly distributed among the components, which is shown in that blue line. And you look at the crossing point and you just choose the number of components that describes more than what you'd expect by that random distribution. So that is the first 4 principal components. The second thing is the number of clusters. So I used cross-validation and tried out various different numbers of clusters and plotted it against a metric of model performance, which is kappa, and I just chose the number of clusters that gave me the highest model performance. So using that, you have your first 4 principal components. Those are the ones that we retained. You run it through the clustering algorithm with those 10 clusters, and you get a map of acoustic clusters like this. We then plot the ground truth points to interpret each of these clusters in order to collapse it down into these 2 categories of sand versus rock. And there you have a thematic habitat map describing the substrate of this area. Once you have this, you can look at the area of each habitat type. So you can see there's about 2.8 square kilometers of rock and 84.2 square kilometers of sand. We can also check how well this classification works. So again, I had that validation transect. And here we have a confusion matrix. So those areas in green over here, that's where the observation matches the prediction. So observation is rock, prediction is rock, observation is sand, prediction is sand. So the green ones are right, the red ones are wrong. And we can use that to look at various metrics of accuracy. The first is just overall accuracy. So what proportion of the observations were correctly classified? And that was about 96.4%. And that sounds great, except for the fact that you'll realize there's a lot of sand. So if you just guess sand on everything, you'd have really high accuracy. You'd probably have probably like 95% accuracies. So we want to look a bit more in detail. So we can also calculate user's accuracy. And that's if you're a map user, you're looking at this map and it says it's a rock, how much do you trust it? How likely is that to be correct? And we can look at that by calculating the row-wise accuracy. So we had rock predicted 16 times, 11 plus 5. So 11 of those times it was correct, 5 times it was wrong. So that means the user's accuracy is 68.75%. We can do that for sand, and it's 97%. The other way we can calculate accuracy is producer's accuracy. So if me as the map producer, I'm given a new observation, how likely am I to predict that correctly with this method? And you can see that it's actually pretty low. It's only 39%. There were 28 total observations that were actually rock. 11 of them were predicted correctly, and 17 were predicted incorrectly. And then on the sand side, it's 99.14. The last accuracy metric, I mentioned it a little bit earlier, is that kappa score. And kappa ranges from 0 to 1, where 0 indicates no better than random chance, and 1 indicates perfect agreement. And it's basically just overall accuracy. And then there's this penalty term that it gives it, which adjusts for what could happen by random chance. And my value for kappa was 0.48. And the general rule of thumb is kappa greater than 0.4 indicates moderate agreement. So it did all right, but not great. We're now going to run through the supervised classification process schematically. So again, you start with this bathymetry and backscatter layer. You then calculate all those various derivative features, the terrain metrics and the texture metrics. And then you plot your ground truth points. And you use this to fit a model. And then once you fit that model, you use that to predict, and you get a thematic habitat map. Now, there's a lot of different models you could use. I specifically use the random forest algorithm. And the random forest algorithm is built on the decision tree. So here is just a made-up decision tree. And what a decision tree does is it searches through all your variables, and then it tries to determine the value that gives the best split in order to differentiate between them. So like over here, you can see that, if there's this high slope value, it'll think it's a rock. If you're having a low slope, low backscatter, so like not a very strong return, and it's low rugosity, so not very rough, it might think it's sand. And it'll run data points down this tree in order to decide what class it is. Where the random forest algorithm differs is rather than just fitting one decision tree, it fits a lot of them. It fits usually hundreds to thousands, and each of them is actually different than one another. So rather than being trained on the full data set, each tree is trained on just a bootstrap sample of the data set. And instead of being able to search through all the predictors at each split, it's only able to search through a specified number of them, which makes all the trees different from one another. And then in the end, it looks at each tree, gives it a vote, and they decide on the class of the observation based on majority votes. So if 80% of the trees say it's rock, 20% say it's sand, the prediction is that it's rock. And this has been shown to work really well. It's less prone to overfitting than the traditional decision tree, and it still retains those good qualities where it's able to predict very nonlinear data and data where the effect of a variable is dependent on the effects of other variables. So we're going to walk through that for the substrate classification. Again, you start with your bathymetry, your backscatter, and all the various derivative features. And there's two parameters that you need to fit for the supervised classification. The first is the number of variables that you allow it to search throughout each split. So again, using cross-validation, I tested out various different numbers of splits and plotted that against kappa and found that letting it search through just two variables gave the optimal value. And the other thing you need to do is determine how many trees are actually in the model. So that there's not an exact value. It usually just represents an exponential decline, where after a certain number of trees, you're just making your computer run longer, and it's not really giving you that much benefit. So I set it at 2,500 trees, because that's where the error rate had kind of well into where it had plateaued. Once you've done that, you can use that model to predict outward, and you get a thematic habitat map. So you'll notice it looks broadly similar to the unsupervised habitat map. We can again calculate the area of each habitat type. So we have 3.5 square kilometers of rock and 83.6 square kilometers of sand. And we can again do that confusion matrix on the validation transect and check how well it worked. So overall accuracy was about 96.9%. So again, very high, but maybe not the best way to test if it's working. So we can do that user's accuracy, which is that row-wise accuracy. So 20 of the 31 times that rock was predicted, it was correct, so 64.5% of the time. We can do that again for sand, where it's 98.62. Producer's accuracy, that column-wise accuracy, we can see that 20 of the 28 actual observations of rock were predicted correctly, so our producer's accuracy is 71.43. And then for sand, the producer's accuracy is 98.12. And that kappa score that takes the overall accuracy and adjusts for random chance is 0.66. And the general rule of thumb is kappa greater than 0.6 indicates what's considered substantial agreement between your predictions and observations. So this one did a bit better. We can then view these confusion matrices side by side, and the accuracies overall are both pretty high. Some things that I'd just like to draw to attention to are the user's accuracy. They're pretty close. It's actually slightly higher in the unsupervised, but not by much. The much bigger difference is in this producer's accuracy. It's a lot higher for the supervised classification than the unsupervised. 20 of the 28 observations of rock were correctly classified, whereas here it's actually getting most of them wrong. And again, that kappa score is higher for the supervised than the unsupervised, indicating better overall model performance. We can compare the areas. So we see that there's greater area of rock predicted in the supervised classification than the unsupervised. And that's actually related to that low producer's accuracy. Producer's accuracy is related to what's called errors of omission. So you'll notice that the observation was actually rock, but it predicted sand more of the time. So it's getting these high errors of omission where it should have predicted rock, but it's not. It's omitting them. And that's what leads to that lower area. Two additional benefits of using the supervised classification, specifically the random forest algorithm, are that you can get this measure of uncertainty over space. So you can see that there's more uncertainty over here. And it does that by looking at each cell. And if you remember that the random forest algorithm has each tree that gets a vote, and it looks at the level of disagreement. So if 50% of the trees are voting for one thing and 50% of the trees are voting for the other thing, it's going to have a high uncertainty. If they're all voting for the same thing, it's going to have a low uncertainty. And this low represents all agreement. This high represents about 50-50. There's a logarithm in the formula, so the values are a little weird, but that's what the values mean. The next thing that it also has is it has this built-in measure of variable importance. So over here you can see the three most important variables were the terrain ruggedness, the slope, and the surface area to planar area. So measures of the slope and measures of how rough the surface was were the most important. And you can also look at where the importance was 0, and anything that was lower than 0 provided no benefit to the model. We could run through the same thing for the biotic habitat, but it would be really, really repetitive, so I'm not going to do that to you guys. And basically, the attached fauna, the sponges, they just followed the rock. There was almost never bare rock, so the maps pretty much follow the same trend. And again, you could calculate the area of each habitat type. FWRI also mapped this area previously. They used side scan sonar as opposed to multibeam sonar. And you can see there's some similarities. There's like this feature over here. But there are some differences as well. The biggest is these blue areas where they predicted low relief hard bottom, and generally it seems to correspond to sand in our map. They did use a bit different of a scheme than us, but still there are definitely some apparent differences. So I just wanted to walk through a little bit of how they did it. They use what's called a side scan sonar, which is different acoustic technology for mapping, and it collects this data over here, the mosaic, and it's analogous to the backscatter image. And you'll remember that I had those various mathematical descriptors of texture. What they do is they zoom in, and they actually just observe the texture. And based on the texture of the backscatter image, they draw polygons around each area and determine what habitat it is. So they can map really fine-scale habitats like that, but it's also very time-consuming, and it can be subjective. So just comparing the two maps, I looked at when they classified something as ledge, 87% of the time our classification said it was rock. For mixed hard bottom, there was roughly a 50-50 split between sand and rock, which I guess makes sense. And then for the low relief hard bottom, that mostly corresponded to sand. So there are definitely some discrepancies between the two maps that need to be resolved. So the key points for this section were that the supervised and unsupervised methodologies both provided broadly similar results. However, the supervised model performed better than the unsupervised approach, and that attached fauna closely matched the distribution of rock. Now we're going to go in a bit to the fish community analysis. And we'll start off with a fun video. So this is the software we use, and those are Goliath groupers coming in. Lionfish down there. Have this school of gray snapper over here. Creole fish, and it's important to note this is not automatically done. This is me or Abby or Sarah going through video and drawing boxes or points on each individual fish and watching it and rewatching it. And what the software does is it records the exact frame of each fish. And we are training something to automatically classify these fish with SRI, but that is not operational yet. So currently it is still watch the video, draw points on each thing. But since we get the timestamp of each fish and we do those habitat frames classified every 15 seconds, we can relate the fish to their nearest habitat frame. So you can see you have a red fish here, two blue fish here, and their closest frame is that first habitat frame. So you would get two red fish and two blue fish associated with that. Here you'd have just one blue fish. Habitat observation 3 would have no fish associated with it, and habitat observation 4 would have two blue fish associated with it. And that gets us from a transect to our very familiar kind of species by site matrix that can go into a lot of standard ecological statistics procedures. It's also worth noting that here is shown our counts, but all the counts were actually converted to densities to adjust for area, changes in area due to how high we were off the bottom as well as how fast we were going, and that's all done using the methods Sarah outlined in her thesis, but I won't go into those too much. So the CVAS transects that I used are, again, these three transects here. They were all daytime transects during the same cruise within a few days of each other, so there shouldn't be too many confounding factors due to differences in time. Again, here is the substrate habitat scheme, and last time for the map we had collapsed it up to just sand versus rock. Relief has been shown to be something that's repeatedly important for fish. So I wanted to include these relief classes. The sample size for moderate and high relief were a bit low, so I just merged those into one class so I could still explore this, but give it a bit more statistical power by upping the sample size. So the first thing we might want to know is what species are driving the overall variation. And to do that, we can do what's called a principal coordinate analysis. So I ran that, and you get these biplot vectors. And these biplot vectors correspond to how important those species are. So you have the squirrel fish, the lionfish, and the sand tile fish really have those longest vector lengths. So those are the species that are driving the most variation within my study area. The next thing we might want to know is, well, are there differences in the fish communities among the different habitats? And to do that, you can run an ANOVA. And shown here, you can see that both the substrate and the biotic component come out significant. Since there were more than two classes for the substrate, there's that low relief, there's sand, and there's the moderate to high relief. You can follow that up with pairwise comparisons and compare each class against each other. And they were all significantly different than one another. So sand is different from low relief. Sand is also different from that moderate to high relief. And low relief is different than that moderate to high relief. So now we know that they're different, but how are they different? And what you can do is you can do what's called canonical analysis to explore that. And the first thing that stuck out to me is this red cluster over here of moderate to high relief observations. We can also plot the centroids for each to just get exactly where each thing is on average. And you can see that the red moderate to high relief is further out this way, indicating that there's more Creole fish, more Spanish hogfish, Goliath groupers, gray snappers. It's also further along the x-axis, so potentially more lionfish and blue angelfish as well. The sand and the low relief rock weren't super well differentiated. There's a lot of overlap, but by looking at the centroids, you could at least see between the two. On average, you have more sand tile fish in the sand, whereas in the low relief, you tend to have surgeonfish, squirrelfish, and also potentially these lionfish and blue angelfish. They're kind of split between the low relief and high relief. You could run through that same thing for the biotic habitat as well. There's a lot of overlap in this plot. They're not super well differentiated. If you plot the centroids, you could see on average there's more sand tile fish towards the bear habitat and more blue angelfish, lionfish, and squirrelfish towards the attached fauna. But again, they're not super well differentiated. So one thing that kind of happens in the background of those multivariate statistics is that they look at fish communities provided that a fish community exists, which means that you need to remove all the sites where you don't have any fish. But that could potentially provide some interesting information. So I plotted the species richness by each habitat type. And you can see that in sand, your species richness is usually 0, like 90% of the time. So that means that there's no fish in the sand habitats most of the time. Whereas once you get to the low relief, even though the communities weren't that well differentiated, you have fish 50% of the time. So there's a big difference in that. Once you get up to moderate relief, you have fish 80+% of the time. You're getting a bit higher species richness, so getting up to maybe 4, whereas here you're getting to 3, and here was only 1. And you're also getting maybe occasionally some even higher values as well. Additionally, you can look at the density of fish. So here's just general density for all fish. And you can see that the density over sand is very low. It's a bit higher once you get into that low relief rock, and a lot higher once you get into that moderate to high relief rock. So you see the general trend of more species-rich assemblages and more abundant assemblages in those more complex, higher relief habitats. You could run that through on the biotic, and you see the same trends where you're getting more species-rich assemblages in that those habitats with attached fauna, generally seeing fish more often, and again, higher density. So that same idea of more species-rich and more abundant fish assemblages with more complex habitats. So the key points for this section are that the main species driving the variation in the study area were the squirrelfish, the lionfish, and the sand tile fish, and that significant differences were found among the fish communities in different habitats. You have more abundant and species-rich assemblages in more complex habitats. And now we will move on to part 4, which is estimating the total abundance. So in the previous 2 sections, I talked about determining the densities per habitat. So you can see the density for all fish was a lot higher over rock than sand, and you could do this also for various individual species. And shown here are the 95% bootstrap confidence intervals, and you can see for certain species they're relatively tight. So things like lionfish and squirrelfish generally exhibited nice behavior for math in the sense that they occurred pretty regularly over rocky habitats in small groups, whereas things maybe like gray snapper, they occurred very periodically in large schools, so low sample size, large variance, higher confidence or larger confidence intervals. So fish behavior can affect the precision of the density estimates you get. Additionally, in the habitat mapping section, we got the area. So if we have the number per square kilometer and the number of square kilometers, I know I've thrown a lot of math at everyone, but I'm going to throw one more math thing at you guys. Use what's called multiplication. And you have the number per square kilometers times the square kilometer gives you the number of fish. So that's a very simple way of calculating total abundance. And when you do that, you can get, here in purple is shown the total you'd expect, as well as how that breaks out by habitat type. And you actually get greater than 50% of the total fish expected in that rock habitat. And that kind of underscores the the potential of these rocky reefs to be essential fish habitat because it makes up such a small percentage of the study area. It was actually only about 4%, yet you're expecting to see most of the fish in that area. The flip side of that is that if you look at just the density estimates of sand, you'll remember you couldn't really even see the bar. It was so low. But because there's such a large area of sand, it still allows it to contribute a substantial amount to the overall populations. And now it is worth noting that these should be total abundance estimates asterisk, because really what we need to do is assess the catchability, which means the proportion of fish that sea bass is actually seeing. And Sarah started to do some of that in her thesis where she looked at attractants and avoidance behaviors of fish in the near field to sea bass and found that most of our study species were either had a neutral response or weak negative response, but there could also be reactions in the far field where they're not in view of the camera yet and they're scattering. And we're working on kind of nailing down what those catchability factors are through paired experiments with FWRI, who does a lot of stationary camera work. Basically, they put down the stationary camera, we then fly sea bass directly over it, and we see what the communities are like before and after. But that is an ongoing thing. So we don't have the catchability for each species yet, but in order to really get truly accurate total abundance estimates, that's kind of the next step. So the key points for this section are first that habitat-specific densities and the areas from the habitat maps can be combined just by multiplication to determine how many fish there are. But accurate abundance estimates really do require a catchability coefficient to be determined. That rock habitat would contain greater than 50% of the total fish, despite only comprising 4% of the area, underscoring the potential of these rocky reef areas to be essential fish habitat. That sand, despite having those low densities, is still expected to contribute a substantial amount just due to the sheer amount of area. And lastly, that fish behavior can affect the precision of the density and abundance estimates, though. That could potentially be ameliorated by differing sample design where you sample those higher variance areas a lot more. And I've talked to Steve about he's mentioned like using some log normal statistic things, which might be able to eliminate some of the higher variance things and tighten those confidence intervals a bit, but didn't do that for this. Lastly, I'm just going to talk about future work. So I'm not leaving. I'm staying here for my PhD. So there's a lot of directions I could take this, and I want to make it clear that I'm not going to do all of these things. There are a lot of things here, and I don't know what I'm going to do, but they're all potential directions I could take it. So first, on the mapping side, we can reduce the uncertainty by incorporating more ground truth data. So I had that uncertainty map. There's still discrepancies that need to be resolved between our map and FWRI's map. And I only used 3 transects from one cruise, but we've collected a lot of data in that area. So these are all the transects we've collected in that area since. So there's a lot more that could be incorporated and see what's going on with those differences and reducing the uncertainty and upping kind of the sample size of those rarer classes. The second thing is integrating these maps with other data we've collected, which include sediment grabs as well as subsurface seismic data. We've also mapped with bathymetry and towed video a lot of other areas on the West Florida shelf, so applying this method to get thematic habitat maps of those areas. Mapping habitats at finer spatial and thematic resolution, so I regridded the multibeam to 10 meters, but ideally we'd be able to use the full resolution of the multibeam, map finer scale habitats. So I did sand versus rock, but there's a lot more on the ocean than sand versus rock, so really getting at those smaller habitats. Incorporating geostatistical methods, expanding it to look across multiple different scales of analysis. On the fish side, I could compare fish communities with the different areas. So, we collect data in various different places and see how the fish communities differ among those. Again, applying the methodologies to assess the fish populations here or communities here in other areas to see if they show similar habitat associations in different areas. Again, incorporating geostatistical methods. A kind of buzzword lately is seascape ecology, and it borrows from landscape ecology techniques. And rather than just looking at the habitat alone, it actually looks at the arrangement of habitats and the area of different patches of habitat. And I was talking, I don't know if Selena's here, but she was talking to me the other day about actually taking the sea bass imagery and stitching it together into one continuous photo mosaic. So rather than using those still frames, we could actually like classify the entire transect potentially, and that could help with some of those like seascape metrics, like the patch size of each habitat. A lot of the data is binned because in order to get it into an ANOVA or a CAP, you need to bin the data. So it's binned to 15 seconds, but a lot of time series techniques translate pretty directly to moving across a transect in space. So really utilizing that full continuous data and seeing what that shows us, including oceanographic variables, whether that's modeled data or data collected by the sea bass. We collect various different oceanographic variables through the sensors we have, quantifying that fish reactive behavior to sea bass to get those catchability factors, analyzing if there's differences in the community by day, by season, or annually, and lastly, modeling the distribution of various species. With that, here are my references and acknowledgments. Of course, my advisors, Steve Morawski, Stan and Ted, who are on my committee, Dave Jones, who's unfortunately no longer with us, but was a really big help on the statistical analysis. The CSCAMP team in general, they are great, and I couldn't do any of this without them. My fellow minions in the Morawski lab, my parents, my mom who's here, and my dad who's watching the live stream. The CMS 2015 cohort, you guys are all great. And all the people in other cohorts that are also here, you're all great as well. Specifically, Kelly was nice to bring the snacks and the coffee, so she's the MVP. So if you guys had any donuts or coffee, that's her doing. The CMS community in general, you guys are all great. I'm sure I've come to you for something, which leads me to my next one. Literally anyone who I've asked for help at some point. Lately, I've been nagging Josh about things, and I've been nagging Sammy about forms. But I've definitely come to a lot of other people, so thank you for helping me. I've been lucky enough to be funded by various fellowships we'll hear, so thank you for anyone who has supported me financially. Thank you to Florida Sea Grant for funding me to go to a conference, and thank you to NCs for giving me a lot of the coding skills that were necessary for actually running these analyses. And with that, I will take questions.